Hi, having studied all the properties of R, namely the order properties and algebraic properties, and discussing some of the inequalities, we are now in a stage to look at how we can have all the real numbers like root 2, root 3 and so on in the set of all real numbers itself. For example, we have already seen that the set Q, the set of all rational numbers, is also having the algebraic as well as order properties as in the case of real numbers, but we have seen that square root of 2, square root of 6 and such numbers are not rational numbers, they are irrationals. So, likewise, we can look at the set of all real numbers where we have all these numbers as real numbers itself. So, the property which is not holding for the set of all rational numbers is holding for the set of all real numbers. So, why is that difference happening? So, let us look into a solution of that. First, we will be discussing what are bounds of real numbers. Let S be a non-empty subset of R. The set S is said to be bounded above if there exists a number u, a real number, such that every S is less than or equal to that particular number u. Then the number u is called the upper bound of S. So, any real number which satisfies this condition, that is, that real number is larger than or equal to, greater than or equal to every element of the set S, that number is called an upper bound of the set S. And similarly, we can define, let S be a non-empty subset of R. The set is said to be bounded below or bounded from below, we can say, if there exists a number L belonging to R such that every element of that set S is greater than or equal to that number L. Such a number L is called the lower bound of the set S. For example, we can see, as we have seen, the real numbers can be arranged on a real line. Suppose we have a set like this, these are the elements of the set S, this is the set of all elements consisting of the set or constituting the set S. Then we can see that there are so many real numbers here which are greater than that set S. Say we can write u1, u2, u3 etc. many elements we can have on the right side of that set S, as well as we can have L1, L2 etc. many elements which are on the left side of that set S as well. So, if there exists such real numbers on the left side and right side of that set S, these are called the upper bounds of the set S, upper bounds, whereas these are called the lower bounds of the set S. So, these are precisely what is said in the definition that we have seen so far. A set S is, it should be non-empty subset. So, it is said to be bounded from above if there exists such a real number u such that every element of that set S is less than or equal to that real number, and a set S is said to be bounded if it is both bounded from above as well as from below, and is said to be unbounded if it is not bounded. So, there can be cases where the set has only the upper bound or the lower bound. Then also we will say that the set S is said to be unbounded. So, for example, we can see the set of all x belonging to R such that x is greater than 2. So, when we consider this set, we can see on the real line we have 0 somewhere here, 1, 2. So, the set x belonging to R such that x is greater than 2 means it has lower bound as 2 or 1 or 0 or any number which is less than 2, but this does not have an upper bound. So, by the definition of unbounded set, this set is said to be unbounded even though it has a lower bound. Similarly, the set of all x such that x belongs to R such that x is less than 10. This set consists of all the real numbers which are towards the left side of 10. So, this is the set S. So, we can see that 10 is an upper bound. Similarly, 11, 12, etc. are all upper bounds of the set, but it does not have a lower bound. So, again, by the definition of unbounded sets, this set becomes an unbounded set. So, in both these definitions or in both these examples, we were looking at the values of real numbers which are greater than or equal to some particular real number and less than or equal to some other real number. So, in this case, as we have discussed, 2 is a number, 2 is a real number which satisfies the conditions in the definition of a lower bound. 1 also is a real number which satisfies the conditions of a lower bound. 0 also satisfies the conditions of a lower bound. So, look at all these numbers which are towards the left side of the set. Any of these satisfies the conditions to be a lower bound of the set S. Similarly, any of these elements on the right side of the set S also satisfies all the conditions to be an upper bound of the set S. So, there is something in particular that we have to look here. If you have U as an upper bound, if U is an upper bound of a set S, so is U plus 1, U plus 2, etc. are all upper bounds. These are all upper bounds of the set S. Similarly, if L is a lower bound of the set S, then so is L minus 1, L minus 2 and so on. That means any real number which is on the left side of L also is a lower bound of the set S. So, there is some interest in finding out which is the least of all the upper bounds, because we have seen that if one element is an upper bound, every element larger than that, every real number greater than that is also an upper bound. So, which is the least of all the upper bounds and which is the greatest of all the lower bounds? That is a question of interest. Now, let us look at an answer to that question. If S is a non-empty subset of R and if S is bounded above, then U is said to be the supremum or the least of all the upper bounds if it satisfies the following two conditions. Which are the two conditions? The first condition being U is an upper bound of S, and if V is any other upper bound of S, then U is strictly less than or equal to V. That means V should be greater than U, or U should be the least of all the upper bounds, and we denote the supremum as SUP of S, which is read as sup S in short. Similarly, we can define the infimum or greatest lower bound as follows. If S is a non-empty subset of R, if S is bounded below, then a real number L is said to be an infimum or greatest lower bound of S if it satisfies the following conditions. The first condition being it should be a lower bound, And second condition, if m is any other lower bound of S, then m is definitely less than or equal to L. Then the infimum of S is denoted by INF of S. So, now we can see that these two definitions, that means supremum of S and infimum of S that we have defined, they are unique. That means, if we have a set S and if that set S has a least upper bound, then that element will be unique. So, let us see, for example, suppose that U1 and U2 are both supremums of the set S, where S is any non-empty subset of the real numbers. If possible, let us assume that we are going to show that there cannot be two supremums. We are going to show that U1 is equal to U2. So, if possible, let U1 is not equal to U2. Then, by the law of trichotomy, what do we have? Either U1 is greater than U2 or U1 is less than U2. So, suppose we take the condition that U1 is greater than U2. So, if U1 is larger than U2, where is U2 lying? This is the set S. For example, somewhere here you have your U2 because U2 is the supremum of the set S and U1 is larger than U2. U1 is greater than U2. So, if U1 is the supremum, supremum means it is the least of all the upper bounds. So, how can U2 be an upper bound for that set S? Because U1 is the least. So, U1 is equal to supremum of S indicates that U1 is the least upper bound, is the least upper bound. So, how can U2 be an upper bound then? Because by assumption U2 is also a supremum of S. So, it cannot happen that U2 which is lesser than U1 can be an upper bound of the set S. Therefore, we arrive at a contradiction. Similarly, you have the same contradiction happening when U1 is less than U2 because by assumption U1 and U2 are both supremums of the set S. So, it cannot happen. That is why we can have U1 is equal to U2 itself. So, the supremum if exists, it is unique. Similarly, the infimum of a set is unique. So, that is the result. Now, let us look at an example where we are asked to find the supremum as well as the infimum of a given set. So, we are given a set S is equal to the set of all 1 minus negative 1 power n by n. So, let us see the set S given here. S is equal to the set of all 1 minus negative 1 power n by n, where n is given to be a natural number. So, starting from n equal to 1, let us arrange these or let us expand this term with n equal to different values. So, first let us put n equal to 1, let us see what this set S is. So, if n is equal to 1, we have negative 1 power 1 by 1 which is negative 1 itself. So, we have 1 minus minus 1 by 1 which is equal to 1 plus 1 which is equal to 2. So, 2 is the first element of the set S. For n equal to 2, what do we have? 1 minus negative 1 square by 2 which is equal to 1 minus 1 by 2 which is equal to 1 by 2. For n equal to 3, 1 minus negative 1 cube by 3 which is equal to 1 minus 1 by 3 which is equal to 2 by 3. and so on. So, now let us see what happens as we move on further and further. What happens when n becomes larger and larger? So, as n becomes larger and larger, minus 1 power n upon n goes to 0 as n goes to infinity. Therefore, the elements of the set negative 1 power n upon n tends to the value 1 as n approaches infinity. So, we have the elements of the set listed something like this: 2, 1 by 2, then 2 by 3 and so on. Finally, we will be getting 1. So, we can see that all the elements of the set S are somewhere between 2 and the number 1, and there is a 1 by 2, 2 by 3 and so on. So, these are some of the values that we have. So, listing all the elements of the set S, we can see that the supremum of the set S will be equal to 2 and infimum of the set S is nothing but half, because all the elements of the set S are less than or equal to 2 and every element of the set is greater than or equal to half. So, we can show that supremum of S is equal to 2 and infimum of S is equal to half in this way. So, that is the method of solving this problem. And similarly, we can do the questions like the supremum and infimum of the set of all 1 by n, also by listing out all the elements like this, and as n approaches 0, we can show that n is going to infinity, 1 by n is going to 0. So, we can see that for the set of all elements of the form, the set of all S is equal to the set of all 1 by n, where n belongs to the set of all natural numbers, will have supremum as 1 and infimum as 0. So, this is another example, because limit 1 by n is equal to 0. Limit n tends to infinity, 1 by n is equal to 0. So, we can list out all the elements 1, 1 by 2, 1 by 3 and so on, and finally, we will be reaching 0. So, that is another example to find the supremum and infimum. Now, we have a lemma in which how can we find the supremum of a set S? A number u is the supremum of a non-empty subset S of R if and only if u satisfies the following two conditions. So, this is another way of defining a supremum of a set S. A number, a real number u is the supremum of a non-empty subset if and only if u satisfies the two conditions. S is less than or equal to u for every element S belongs to u S, because u has to be an upper bound, and if v is any number which is less than u, then there exists at least one element S1 in the set S satisfying the condition v should be less than S1. So, why do we require these two conditions? Is because by definition of supremum, u is a supremum if it is the least of all the upper bounds. So, it should be an upper bound first of all, that is why we have the first condition, and second condition is that whenever we have an element v less than u, that means if an element real number which is less than u cannot be an upper bound of the set S. That is why we need, in particular, there exists at least one S1 in the set S such that v is less than S1. In a more geometrical way, we can look at that condition as follows. we have the set S as we have drawn in the first case, we have this set S here. We have the least upper bound as say u somewhere here. So, if we have any element v which is less than u, v cannot be an upper bound because this is the least of all the upper bounds. There is no gap between u and the elements of the set S. It is just next to the set S. So, if you have any v element of real numbers which is less than u, definitely there are some points in the set S which are beyond the number v. That is what is exactly written as there exists at least one S1 belonging to S such that S1 is larger than v. Otherwise, v happens to be an upper bound, and so v is less than u means v is the least of all the upper bounds. So, v has to be equal to the supremum. So, that cannot happen because u is the supremum. So, definitely there exists at least one S1 which is greater than v. So, this is an alternative definition for supremum of a non-empty set S. And keeping that definition, that alternative definition, we have a lemma which states that an upper bound u of a non-empty subset S of R is the supremum if and only if for every epsilon greater than 0, there exists an S epsilon belonging to S such that u minus epsilon is less than S epsilon. So, let us look at the proof of this theorem, the proof of this lemma. So, first we assume that if u is an upper bound, we are discussing the proof of the lemma. Let u is an upper bound of the set S satisfying the condition that, what is the condition given? For every epsilon greater than 0, there exists an S epsilon. There exists S epsilon belonging to S such that u minus epsilon is less than S epsilon. So, what we require to prove is, we have to show that u is the supremum. To prove that u is the supremum of S. Now, by the previous condition, what is required to prove? Any element v in R which is less than u cannot be an upper bound, because by assumption itself u is given to be an upper bound of the set S. So, what we require to show is that for none of the real numbers which are less than u can be an upper bound of the set S, then definitely u becomes the supremum. So, let v is less than u, then definitely u minus v happens to be greater than 0. So, let us take epsilon to be equal to u minus v. Then what happens? By the condition given, for every epsilon greater than 0, there exists an S epsilon belonging to S. So, this shows that this is greater than 0. So, there exists an S epsilon belonging to S such that u minus of, your epsilon is u minus v now, u minus v is less than this S epsilon. Now, what is u minus of u minus v? That is nothing but v. So, that means v is less than S epsilon. So, reading together, what do we have now is, let v be less than u, then there exists an S epsilon in S such that v is less than S epsilon. So, reading these conditions together, you have, there exists an S epsilon belonging to S such that v is less than S epsilon means v cannot be an upper bound. Therefore, v is not an upper bound of the set S. So, v was an arbitrary element less than u. So, v was an arbitrary real number. So, that shows that none of the real numbers which is less than u can be an upper bound of the set S. So, what does that indicate? U should be the least of all the upper bounds. So, that means u is the supremum of S. Now, to prove that if u is equal to the supremum of S, this S should be small letter, supremum of S, then what you are asked to prove is, or required to prove is, given any epsilon greater than 0, there exists an S epsilon in S such that u minus epsilon is less than S epsilon. So, that follows from the definition of supremum itself, because u is given to be the supremum of S. Therefore, for any epsilon greater than 0, this is what is asked to prove that. So, since epsilon is greater than 0, u minus epsilon is definitely less than u, because since u is the supremum of S and epsilon is given to be greater than 0, u minus epsilon is strictly less than u, and therefore, u minus epsilon cannot be an upper bound, which indicates that there exists at least one element S epsilon, element of S, such that u minus epsilon is less than S epsilon. That means u minus epsilon is not an upper bound. So, that is what is required to prove. So, this completes the proof of the lemma as well. And in the next session, what we are going to prove is what is called the completeness property of R. That means whether any subset of R has a supremum, which is bounded above has a supremum in R itself, or it is outside R, or where is the position of that supremum, and so on. And before concluding, we can discuss something about maximum and supremum of a set S. If the supremum of the set S belongs to the set itself, then the supremum is called the maximum, and if infimum belongs to the set S, then it is called the minimum of the set S. So, that is what is discussed in this session, bounds. Thank you.